So INL HPC Systems, we operate multiple petaflop systems. We just gave the University of Idaho, Boise State University, and Idaho State University a 1 petaflop system, Falcon. So that's this system here operates, it gives about 220 million core hours a year to users, which we hope Professor Etienne and others will really fill up. They also have access to Sawtooth, which is an InfiniBand-enabled Intel chipset, about 100,000 cores. We run a lot more memory just because we support nuclear energy, so more memory per core. That tends to bode well for the Einstein Toolkit users also, which kind of be heavy on the memory usage. We also have LEMHI. These are all named for locations in Idaho, mountain ranges, usually what we pick for names. About 20,000 cores. Notice we use OmniPath on LEMHI. And this is what's really motivated a lot of our investigations into containers. We have some, and of course we have Falcon. We have some major HPC systems with different architectures. We don't even run the same operating system on. So we're Rocky Linux on some, CentOS on others. We'll have AMD systems. We'll have different generations of InfiniBand, different generations of OPA drivers, different generations of Mellanox drivers. And essentially we have kind of a heterogeneous mix of mostly CPU computing, as we're mostly a CPU computing shop. The nuclear energy industry tends to be conservative. I think you should all be grateful for that. And so we tend to be mostly not a GPU shop. That kind of fits well with the Einstein Toolkit, maybe not so much in the future, but at least for right now, for those of you who use INL, we hope we'll have more of you using this. We're all liquid cooled. 3 petabytes of disk storage. We're getting another couple of 3 petabytes in the next 2 months or so, so we've got lots of scratch. We have about 1,200 users, and about 300, 400 of those are university users. So that's kind of where we are. So let's talk about containers then. So why did we start looking at containers? We're obviously very concerned about verification validation. We're concerned about transient testing and making sure that everything is absolutely correct, that there's no artifacts in simulation. We want everything to be 100% reproducible. And for some of our experiments that we support, they have to be reproducible for up to 10 years after the initial simulation existed. Now, for most of us in the relativity community, a simulation that was run 10 years ago, it's very likely you're going to be able to run that out of the box again 10 years later. There may be some dissension on that, but generally that's my anecdotal impression is generally running a simulation that was for, say, a publication 10 years ago, it's kind of difficult. It takes some work to get those things to happen again. In our case, there might be a regulatory requirement to be able to support a simulation that's 10 years old. How do you do that when the technology is changing, when the drivers are changing, when the operating systems are changing? Even sometimes when a system administrator does an update on the HPC system, does it break your code? Anyone raise their hand? Has that ever happened to them? Okay. So this is why we started investigating containers. But we want to think about containers in a high performance computing sense, in which we want MPI to launch the container. And we want it to make it a whole lot easier for us, for our Windows users. Again, most engineers, nuclear engineers, are almost all Windows users. Now, in the Einstein relativity community, we're probably more Linux heavy, but there's probably a couple of Windows users out there. We want everything to work the same everywhere. We want to insulate people from these silent limitations. So why would you look at a container? Verification validation is probably #1 reason. Is my code running correctly still? Still passing all the unit tests? Can it give the same results as my last few papers? And is it easy to do that? It should be easy to do that. In fact, it should be transparent to be able to do that. Sometimes we like to talk about storing data. So I'm going to store data for the next 10 years. Okay, so data storage is probably going to run between 5 cents a gigabyte per month to about 20 cents per gigabyte per month, depending upon what sort of a solution you go to. If you move it in the cloud, every time someone touches it, it's going to cost money too. And so you have to have a credit card to be able to access that data. Does it make sense to store terabytes of data from your last binary black hole merger for 10 years so one can get it? Or is it easier just to create a container that they could run and recreate the data? Cycles tend to be cheaper than storing data for 10 years. So that's kind of what that line of thinking goes. Reproducibility equals, can I run my same application 10 years later? For the Einstein Toolkit, probably not as important, but for other fields, it's really important. You want to make sure that everything is working right. Portability across multiple supercomputers. This was the topic that really motivated us to look into it. So we have multiple different types of supercomputers, different fabrics, and of course we see, that things are getting more heterogeneous in the future. We see Cornell, we're seeing OmniPath is resurrected. It's still there. You can buy it again. from Cornelis. We've got InfiniBand, lots of different variations of InfiniBand. We've got Gigabit Ethernet's back. So lots of different features. And we want to be able to run a code or a set of codes, develop a set of codes that are going to run on your Windows box. And then they're going to move to a supercomputer, move to another supercomputer, and be able to not have to change it and not have to recompile. And be certain that we're going to get the same results in every single location. That was our main thing. Now, simplification, it is always irritating when somebody, you work in one environment, maybe you get used to Rocky Linux and you go to CentOS and discover all the stuff you wanted there to compile your Einstein Toolkit's not there anymore. Or maybe Qubit's not there, and so, oh man, I got to install that now. Maybe somebody goofed up to install, and made it a pain to install later into a pound environment. So simplification, one environment, customized packages, independence from the system administrators. That's why we look at containers. We want to get away from letting the system administrator have to do things, install everything, set up everything properly for us. So we work without the need of intervention from the system administrator. That's always a question you should ask yourself when you run an HPC system. And if not, maybe you need to think a little more about containers. Security. All right, so the security landscape has changed enormously, and it will change significantly in the next 2 years. Okay? So big changes coming, lots and lots of things happening. HPC security is accelerating at a pace not seen before. That means you're going to see a lot more critical updates, a lot more critical patching, a lot more regularly, sometimes in the scale every week. Things are going to change, which means your code that you've so meticulously compiled and fine-tuned and set everything for will all of a sudden no longer work because somebody decides that the TI-RPC library is no longer supported or is a security risk. These things will happen, they will accelerate in the next few years, and they may sabotage your PhD. And so think about that. And the nice thing, this is just new, is you don't have to be pseudo to build a container anymore. Hey, that's great. So anyone can build a container. So that's pretty cool. Now I have to admit that's a beta release feature, but that's pretty cool that that's coming down the pipeline. So this is why we talk about containers. Let me give you one way to think about containers. So the way we've approached containers, we want a container that will be able to at least, I may have skipped a, okay, I didn't, okay. So we want a container that can be a recipe for a container that can be built even 10 years from now. So it's not just building the container and then having the container in some repository you can download and run. We want to be able to reproduce the containers whenever, all the time, and to be able to deal with issues like new drivers. So we're not entirely dependent upon, say, AVI compatibility in different MPI versions. So the idea is container layering. This is a concept really introduced in Singularity, but you can run a Docker too. There's lots of capabilities. You have a base OS container, extremely bare bones. You pick the operating system you want to work in, maybe Ubuntu or Rocky or whatever else you want to work in. That's you get a bare bones operating system. You add a second layer to it, the operating system plus. So you add in your tools, your compilers, Vim, maybe a visualization, maybe add in Qubit, add in Paradigm. And then you have a base OS++. So this is the container plus++. That is you're adding your MPI. Okay. Now, granted, that will change over time. Your container will not live 10 years unless you have the ability to add in this last container to be able to change the recipe and add in, adjust the last piece of the container, the base plus container. The other pieces can stay the same, and they can really live for 10 years. So this is how we give longevity and reproducibility to our containers. So each stack of the layer is reproducible, with the final stack being the one you're going to have to change every 2 or 3 years. But that's pretty easy through layering. So how do we typically build a container for HPC? Okay, you've got a Docker repository, Singularity repository. You pull a whole bunch of containers. Notice I made them all black boxes, right? But you don't actually know where these come from or anything. You pull a bunch of library containers from some location that you kind of hopefully trust. You can't really always reproduce. And then you make you build your container, and your container's there, and then you can make it available to your graduate students, to your friends, and they can run the Einstein Toolkit without having to build it. But then something breaks and it's not reproducible, and it's kind of a pain. That's how people normally build a container. Of course, there is another way. So this is kind of that process where you end up with a build. You have a black box at the end. We want to get rid of the black box. We want this to be fully, easily reproducible. So Since we are calling from the cloud, generally what happens, that space might not be reproducible. That's bad. That means your code is not going to work in 10 years or 5 or even 2, right? So there might be a git clone in that recipe file that could change. If you package install, apt install Python won't always give you the same version of Python, right? So you've now created built a container that's a black box that's unreproducible. You want to avoid that, especially if you want to do binary black hole mergers or neutron star black hole mergers, and you want to be reproducible, and you don't want to store terabytes of data. You want to give them a container that can be easily reproduced 10 years from now, and people can reproduce this data without having to store terabytes of data. Okay, so there's 2 approaches to how you deal with containers with InfiniBand or with MPIs. Okay, there is the bind approach and the hybrid approach. I'm going to give you demos of both. We'll do them live on the INL HPC Systems. But first, let's go talk about the bind system. This is how we typically think about containers. This means you install the system MPI and the system InfiniBand drivers or Omnipath, whatever you're working with, in the container itself. Put it right in the container and you bind it right there. So if you do this, this requires that the host operating system and the container operating system have to be compatible. So don't try this on a Windows box. Build your Einstein Toolkit and put it on a Windows box. It's not going to work. Right? Just won't work. This is a approach. Many people have tried this approach. It's generally not scalable either. The hybrid approach is what I'm going to propose as a solution. And we've been working on the Einstein Toolkit now for about 3 weeks. So not long. So I don't have that container ready, but we'll have it ready very soon. And we'll make it available. So the hybrid approach is where you put the system, you have a system MPI. Of course, if you run on an HPC system, there's always a system MPI. There's a container MPI, and those do not have to match, nor in version, nor in flavor. You have to be ABI compatible, that's it. You have a system InfiniBand, you have a container InfiniBand. Again, don't have to match, not even version number. That's pretty cool. That insulates you against updates. Okay, so there's no need to recompile all the containers if something changes on the system. Somebody does a security update, it doesn't affect your runs at all. They run exactly the same. So you can have Ubuntu in the container, you can have SLES on the system. And we heard yesterday, Roland mentioned a little about compiling the Einstein Toolkit on Windows. I would never try that. I would put it in a container in Ubuntu and run it on Windows. And that'll work just fine. And you'll never have to worry about it again. Or Rocky. So let's say I can't stand CentOS. And I'm not saying that I don't like CentOS OS, CentOS, but let's say I just decide to run Rocky Linux every time I run on CentOS 7, right? That's a real solution. It's a viable solution. You'll never have to deal with the pain again of working with CentOS. Thank goodness it's end of life. Okay, so the MPI for the system and the container must be ABI compatible. That means you can have Intel MPI on the outside in the system, and you can run MVAPIC. Or you can have MPIC in the system, and you can put MVAPIC in your container. Or anyway, you can put Intel MPI in the container and run MVAPIC on the system. It just has to be ABI compatible. Question?
So this is an MPIC family only, right? No OpenMPI.
OpenMPI works too. Yeah, well, OpenMPI is not ABI compatible.
That's what I'm thinking you're.
Yeah. So you do have to have 2 different containers on the last layer for MPI, OpenMPI versus MVAPIC. Good catch. Yeah, go ahead, Roland.
So if you have time for a question. So you're basically with the hybrid approach, you're basically running the external MPI, but you're binding to the inside because that's the ABI. That still means if somebody updates the outside MPI and puts in a new bug, then it suddenly no longer works.
So we're not selling snake oil, right? If there's bugs on the outside, it's still going to be, fix that. MVAPIC too certainly has bugs in the eager release buffers. They're definitely still there. Hopefully they'll fix them in the next release. And we're working with them on it. But in terms of that's why you do layering, to protect yourself against this. So when you rebuild the container, it's just the last layer you change. So it's a real simple recipe file. Everything else stays exactly the same. It's in the performance. Well, we'll look at the performance. It's actually pretty good. And that's why we're moving all our codes this week. So yeah, you're right. ABI compatibility. You're right. The IB driver does have to be series compatible. There's a bug in the system series. You're going to still have that. They update it. You just change the last layer if it's not series compatible. And we find that generally doesn't happen on time scale 3 years or less. So generally, your container you're going to build, it's going to be around for a while. And longevity, well, when it does change, you move to a vastly different supercomputer, maybe completely different driver series, you can actually just layer the last container and everything will work. Simulation will still run as before. And guaranteed give the same results. With the caveat of any bugs in the series ABI, in the series IDBI. Okay, so for example, you can have MPIC in the container and Baptist2 on the system. That would work. Hey, this solves a lot of my problems, right? Because I've got systems that have got OmniPath, I've got systems that have got InfiniBand, I've got systems that have got weirder stuff than that. Okay, so that's pretty cool. That's neat. So what is? Let me give you an example of what I mean by layering. Sometimes the word is chaining. Sometimes that's used. So we start off with our blue box. This is our base plus container. I'll give you an example, and then I can actually build the next container with the different MPI versions. And then I'll just pick that orange color since I work with the orange, or I guess I picked the green one. So I start with MPI version B, and then the next step, I can go ahead and put the app right onto that layer as the next layer of the container. So we're going to do a little demo here. I'm doing my phone. So this is a base container recipe file. This is probably the easiest recipe file. I'm just pulling Rocky Linux 8.5 here. Bare bones, nothing else. Pretty boring. Okay, so that's your base, that's base layer. Okay, now, and what we do to insulate ourselves against changes against, say, operating system, we just pull the whole repository and we'll just host it for 10 years. The entire repository for the operating system we care about, that we work with. And that's not a lot. It's not a significant amount to store for a long period of time. So in case Rocky Linux 8.5 ever disappears somehow, or you can't get the code, we've got it. Okay, so now here's Bootstrap. Here's layer 2, I think they call it. So I'm going to build off of the base layer, local image. Oh, look, I've installed Fortran, GCC, Vim, wget, just some other stuff. That's my next layer. I can now build on each one of these layers. I can change these. Okay, next step. Now I'm going to add, well, that's the same slide again. All right, well, now I'm going to build from my last one, dependencies. I'm going to make a new one. I'm going to go ahead and add my OPA fabric, drivers, firmware, some other stuff. So I'm basically installing OmniPath. So this is for servicing OmniPath MPI. Then I'm going to my last one. I went ahead and put the application in this layer 2. So you can take a look. I added an MPI forward. And that's the demo we're going to use. We're just going to run it on multiple nodes, and we'll just have it clean out its way. Okay, so I install HWO. I go ahead and I grab OpenMPI. I actually grab them in this container. Put them both in there so you can have access to it. So the container recipes are actually pretty simple. And from this, I can now reproduce this for 10 years in the future. That's the claim. But I can take this setup, and I can run this exact same code on whatever supercomputer they throw at me 10 years from now.
Except you're opening a URL. It might not be there.
You're right. So I better take back my point. That was, yeah. So okay. I did not grab against the local repository there. Good point. So normally we could grab everything from our local, put it on a local repository and then grab it. I know it's always going to be there. You're right. First, I kind of hope that OpenMPI will still be around in 10 years.
Yeah, but maybe it'll be called FOpenMPI.
Roland is shaking his head, so maybe no. Okay. All right. Well, that's the little recipe file. Let's go ahead and do a demo now. So I like demos. Let's see if I can get this out of the way. Okay, we are logged into the INL HPC Systems right here. And hopefully you guys can see my screen. I guess, can I make this bigger? Let's see if this makes bigger. Nope. No.
Are you running Slurm?
I run Slurm and PBS.
And PBS.
We do both. And we have our own scheduler too. So. We have all sorts of fun stuff. Okay, so let me go ahead and unlock my system. Just a minute. Okay, so what you're looking at is we have all the different, they've already been pre-built, these containers that I just showed you a minute ago. Let me go ahead and run the base container. So if I just run this base container, it will actually just put me in a shell directory. So I'm running a singularity. Okay, so I can get out of that container here, Control C. Okay, so let's go ahead and you can see, let's go ahead and I can do singularity, execute. base layer CIF which vim. Now vim shouldn't be there. And so I should say it didn't even find which. So this is a very, very bare bones operating system image. Let's go ahead and do the next one now. So I could do singularity execute 0, 1 dependencies, which vim, and hey, there it is, there's vim. So I've got vim installed on there. And we can double check that. Let's see if GCC is there. I didn't install any, I think I actually did put the compiler there. Yeah, there's the compiler. So it's the compilers and the right version and everything is there in that layer right now. Okay, so let's go ahead and go to the next one now. Singularity. So this is demonstrating chaining. This is what buys us longevity in the container. So this one, O2, is we're going to go ahead and look at the omnipath, which OPA info. Hey, there it is. Got the OPA drivers in that version. Now let's go ahead and look at the last piece of it. O3 MPI omnipath, which MPI CC. There it is. MPI run should be there too. Hey, there it is. Okay, so now that is, I've got all my images built. These are gonna go on forever. Go ahead. I wish I could. Yes, exactly. Exactly. There you got it. It's a simple idea. I have no idea how to make a terminal.
I'm thinking if you right click on the little icon there,
Maxim.
You got properties.
Oh, let's do that.
And then
font.
Font. There you go.
Oh, this sounds encouraging.
Oh yeah.
Just click OK.
Just click OK. They should be good.
Hey. I know how to use Windows. This is wonderful. All right. So now I'm going to run a case. All right. So in this case here, this command, I'm going to go ahead and run. This is the case that's binding. This is how we typically run a container. So I've got Singularity execute. I'm running my container, which is running Rocky Linux. It's the exact same as I'm running on the system. So anyway, and inside the container, I'm doing MPI run -4, and I'm running my total order test. This one actually requires the OS to be completely compatible, and it requires everything to be compatible. So that'll work. All right. That was actually just running on one node, right? So not that interesting. Now let me give you a demonstration of what happens when we do the, okay. So this is the case where I'm doing the hybrid approach. This is the approach we're following at Idaho National Laboratory. And we're testing out for the Einstein Toolkit. This is going to be the approach we like. So here, I'm doing MPI run. I went ahead and give 2 different nodes. I'm just going to run on 2 nodes, nothing big. I'm just going to put 2 processes on each node. And I put, so the MPI run, all of this stuff up to here is just standard MPI, right? There's nothing unusual about this here. Now, instead of launching the Singularity container, I'm just going to run Singularity. Instead of running an executable here, I put Singularity run, and then I give it my container, which is an operating system image that may not even be the same as what I'm running on the MPI. And it may not even be the MPI, the launch list may not even be the same MPI I'm running there. So I have a lot more flexibility now between the systems. And I don't know, I didn't actually check if anyone's running on those nodes. So if anyone's running on them, sorry.
So I'm confused about how that works.
Yeah. So I just ran a distributed run using a Singularity image. I was launching that from the logging node.
When it launches that omnipath CIF,
yeah,
there's some kind of startup script in there that's.
Yeah, it's when I set up the Omni. Let me show you here. If I just run this by itself, it's just going to run MPI hello world. That's what I set the container to do, and just run in 1 rank.
And okay, so the way this is this an MPIC or an open MPI?
This was an open MPI.
So it's figuring out what to do based on the Swarm environment variables.
In this case, the MPI run here, when I compiled the MPI run, this MPI run, which is open MPI here,
right?
That one, I bound it to PBS. And so I could do, but I'm actually specifying the host file, so that it's not even using that binder.
I'm just a little confused as to how it knows what to do.
How can you mix up the different MPI players with the
Yeah, well,
so they're compatible, you can mix them.
So normally when you start up MPI, right, it's got some other funny process that starts with its target names. But you're using MPI run to run MPI run.
Using MPI run to launch the container, which is then passing along that it gets.
But inside the container, you're calling MPI run.
No.
What are you calling inside the container?
And so it's running just this single process. So it's actually passing the MPI information directly to the container. So here we go. There's no MPI run there. It's actually just running the hello world.
So just a binary hello world.
Yeah, just binary hello world.
Okay.
Now you can do the same thing with Thorn. I build, that's why I asked you for that parameter files. I wanted to build an executable with a relevant Thorn list in it from Einstein Toolkit. And then we just build a container. Then you never have to build it, right? Go ahead, question.
I'm still a little confused
Okay.
about the same thing. Because you can specify a different OpenMPI version.
Different version.
In the container.
Yeah.
So then it's like you're still opening MPI to then change.
As long as they're serious. So you can actually change if they're API compatible, it'll work. You can use an older version of MPI inside. It's pretty cool. This is the way you get flexibility. Go ahead.
And I guess just to be clear, the open MPI that actually runs is the outside.
It's the one on the system. That's right.
The outside one. So however old the one on the inside is, because it's API compatible.
It's the one on the system that's actually doing everything. So you hope your system administrator did everything right in setting up the system MPI, which they usually do. This insulates you against versioning issues. And it saves you from having to recompile it, just doing a layer to address non-API compatibility. Okay, so getting puzzled looks, I swear it's true. It does work, and it works amazingly well. So let me see if I got another example here. So this is the.
Well, he is doing it.
Yeah, but if you recall, singularity supports, you can just do every library.
Okay, let's go ahead. I'm going to really blow your mind out. I'm going to go on to a different supercomputer, and I'm going to run the image there across nodes. So Sawtooth. Does anyone here run on Sawtooth? A couple of you. Okay, thank you. We like Sawtooth. It was delivered in the middle of a snowstorm. We were lucky it was delivered. One of those terrible snowstorms that filled the streets. Anyways. Okay, let's go ahead and do this one now. MPI run. I'm going to run the container now. So I'm using MPI run that's on Sawtooth, not the one that's on Limhi, right? This is a completely different operating system too, by the way. This is running CentOS. And my Docker container was built on Rocky Linux, completely different operating system. Okay, so now I'm going to specify my nodes here. Now I have a terrible track record with live demos, so we'll see how this goes. But I still like doing them because it makes it exciting, right? Nobody really knows what's going to happen.
It's going to work.
Is it going to work? What excuse is he going to give if it doesn't, right? Let's see here. I better tell which one to do, which example we're on to. Test. Oh, I forgot to change my key after the last update. I can see. No big deal. There it is. It worked. So I just ran a Rocky Linux container on CentOS 7. Completely, just 10 minutes. All right, well, I think we'll call it good. All right, so that's the story. Containers. So we'll go back to the slide. Oh, I guess I should show one other thing here. So that's the demo. Where did my Chrome go? Okay, here we go. This is what I kind of like about this. This is how we access the HPC systems. So hopefully you'll access very soon. We run Open On Demand, just wrote a paper on it, and we found it has a significant impact on HPC users, especially Windows users. They tend to use HPC a whole lot more, like factors of 3 more if you have Open On Demand available. And so that paper's coming out in PERC in another 3 weeks or so. But so we run Open On Demand, and I'll just show you here. We have a, I guess I should hit a net, right?
I just hit it.
Okay. So we can launch Jupyter Notebooks directly on nodes. You can request a whole bunch of nodes and run Jupyter Notebook. Let's see, I guess I already, that's my virtual Linux desktop. Here's something that's kind of cool. So we added this recently. We can, of course, run Jupyter Labs, Jupyter Notebooks, but what's kind of cool is, here we go. I can select a container, and I can launch the container in the Jupyter Notebook. And so now I can take my container that's been built on the Einstein Toolkit or some other code, and I can request a couple nodes, I can request GPUs, and I can actually just launch the built container with Qubit in it, with ParaView in it, with the right thorn list, everything compiled. And then your Jupyter Notebook, I know Matt Dewey said he didn't like Jupyter Notebook. You can do command line too. But if you like Jupyter Notebook, you just launch it, it's all compiled. And then it's just shift enter to execute the cell. And the whole thing's done. So this is kind of a nice way for people who aren't really big into Linux, and there are a lot of them out there that will say, oh, and they don't even know they're running. They don't even know what they're running, right? It's an the operating system is what you chose, the one you chose to support. It's in the container. I can now just launch it directly as a Jupyter kernel from Open On Demand. And Open On Demand is now being used on, I don't know how many data center sites, but that's where everyone's going. That's the future, it seems, because people are adopting HPC because of it. So now I can run I could add, did not, add the Einstein Toolkit container to my Jupyter kernel, and you can just launch it. And I say, okay, let's say I need 100 nodes. Launch it there. Running is no longer having become an expert in OPA and all the different compilers and particular operating system. I never have to compile anything on Windows again, which is a big plus. Not that it was a drawback for any of you, but that's, anyways. Okay, so that is, I think that's, let me see if there's anything else I was going to mention. Oh, well, Roland mentioned FPGAs yesterday. I happen to be a big fan of FPGAs. You can support FPGAs this way too. That's really cool. Anyways, you can put pedal Linux in those things. Not that any of you will want to do that, but if you want to go the FPGA route, hey, there's a lot of cool stuff there. And I guess the last point, if you're doing GPU work. So containers are kind of, this is maybe how would you say it? Maybe a circus show. I don't know, containers for this aspect. For our purposes, it's really important because we need reproducibility for the next 10 years. We got to be able to have codes that can still run and redo these simulations 10 years from now. For the Einstein Toolkit, that may or may not be important. I personally think it'd be cool to be able to run, the BSSN simulations from 10 years ago and just pump up the resolution, right? Run it again and say, I wonder how close they were to getting it right if I took those kids 10 years ago and just ran more resolution because I got more computing power. Wouldn't that be cool? I think it'd be cool. Some of you are shaking your heads. I do not want to run those codes again. I can understand that, but it's nice to have reproducibility, to know that you could 10 years from now, when all of you are professors at University of Idaho or some prestigious school somewhere, you can say, you know what, I can run my dissertation code again, and I don't have to spend 2 days figuring out how to compile it again or get everything updated. I can actually run it instantly. That'd be kind of neat. So, but that's again kind of a horse and pony show. The more interesting part is the GPU side. If you're working with GPUs, containers are almost a must. The driver variability, the complexity of running the systems with GPU, you almost have to have a container solution in place. NVIDIA's already kind of roadmapped that out quite well. So that's just a thought about containers. I am done with my presentation. Let me log out of these things. Do we have any questions? Lots of questions. Who's the MC?
Oh, yeah. You're welcome to point at folks as you like.
Okay, let's start over here.
My next year GPU. This might be a misunderstanding on my part, but I thought with PIDA and some GPU, you can initialize it and then open up MP or something, a CPU parallelization. So would that be?
You have to try it out. I'd be surprised. So we could try it.
Yeah,
I don't know.
I'll hit you up for the coffee break.
Feel free to ping us.
Yeah.
We're meeting with NVIDIA on Thursday. So I can ask them directly too. I don't know. I haven't tried it. Okay. Yes.
I was wondering how the container itself creates such an environment.
You saw the recipe file. That didn't feel good. Oh.
No worries.
Yeah, so it's like you take a snapshot of the whole operating system with all library and
that's it's very, very limited, right? It doesn't even have PI, right? This is pretty, it doesn't have which in it. This is a very small, lightweight base operating system that we're launching as our executable. Okay, next.
I was just curious, do you see performance difference between running natively and running?
Nope. I can't show you those numbers. Sorry, but there's.
I have a follow-up question on performance because I spent a lot of time fine-tuning my for each single supercomputer to ensure I get the best performance. One computer.
So you don't sleep at night in about company,
When one supercomputer this means using the Intel compiler, this flag, this local flag, other supercomputer, it's something else. Whereas it seems that here I have all the ones. Choose GCC and reuse GCC.
Yep.
But this is probably not the best solution for it.
well, you can use Intel, you can Intel compiler. If you can put
Yeah,
that.
but if I build my computer using GCC, but the best solution would be to use ICC, then I will have a problem.
Well, you can build ICC in a container.
Yes, which means I'll have to support every single possible compiler, single possible combination of flags to have the maximum performance for future computer.
So how much does this equivalent require getting?
Which can be weeks
So-
of calculation. I don't know, maybe expect 12 versus.
The answer to that is that that's the chaining or the layering. So that, supercomputer comes out later and you say, okay, this supercomputer doesn't do as well with the flags that I initially built. You're just changing one piece, one layer of the container. Save yourself a lot of work. But you're right. Containers by themselves they won't give you longevity. They're not going to let you run 10 years. Your same container won't run 10 years from now. But it is the layering that will allow you to do that. And so that will protect you against the changing architecture. That help?
Yeah.
Okay. Yeah, if you're running on, even now, you probably should be hitting containers pretty hard in terms of, I saw the Spectre code, which our speaker spoke earlier. Container. Other questions?
Yeah, we have 2 minutes. Now, suppose I actually want to make use of this for my own code, and I'm not a supercomputing center who can afford to host my own operating system. I want to piggyback on the hosting.
Well, yes, absolutely. But also in terms of hosting is not wild. So we do host, we keep everything, right? That's because we want longevity.
Yep.
Our repos, I don't think they're public right now, but there's nothing they can't be made public about it because it's just, no one's asked us. That's there's other people doing the same as us. So we're not the only ones out there saying, I'm going to grab all of Rocket Linux 8.5, 1.6.6.3 to make sure I have that so I can use it.